And we will continue talking about NWChem and input files, but we will go into a more advanced level of comparing Hartree-Fock and density functional theory and going into time-dependent density functional theory calculations. And so the NWChem mailing list, if you want to use, if you have questions about NWChem, they are usually very responsive to questions sent to the mailing list. And you can subscribe to the mailing list using majordomo@emsl.pnl.gov. And the body of the message should be subscribe NWChem users. So when do you want to use NWChem in games, for example? That was one of the questions last week. When you have a machine with a lot of memory, when you want to run plane wave calculations, when you're running into disk problems with other programs, when you need to run a CC-SDTQ calculation or one of the many other theories that aren't available elsewhere, and when you are using the IBM Blade Center. So NWChem is better in these. So here is the IBM Blade Center, for example, and the methods available in NWChem are Hartree-Fock DFT, SODFT, MP2, CAS, TD, DFT, CC-SDT, CC-SDTQ, non-canonical MP2, MP3, and NMP4 calculations. And then we have relativistic effects, plane wave basis sets, classical molecular dynamics options, and CC-SDTQ dipoles. And you can also conduct classical molecular dynamics or Monte Carlo simulations as well. So the input format used when you start a new calculation, you write start, not to restart, but a start when it's a new calculation. Then you give the input file's name, and then you give a title usually. Then you give the geometry information, and then you can give the basis set information. Here all atoms are chosen from the library, and the basis set is 321G. And semicolons can replace new lines. So you can write, for example, here MP2 semicolon freeze atomic, and then semicolon end. And you can specify a task, what the NWChem should do, or you can specify more than one task in one input file. So input format number is common character. Directives are read and tasks are executed in the order they appear in the input file. And some of the input directives are echo, that copies the contents of the input file into the output file. Scratch directory is sets the location of the scratch files. Permanent directory is the location of important summary files and database file for restart. That's very important. And the title, it's an optional title, can be given to keep track of calculations. Start is for starting a new calculation, initial calculation. Restart is for extending a calculation or restart a calculation using the information from the DB file. And the memory specifies the maximum memory usage. MP2, it's control MP2 related options. CCSD defines CCSD related options. DFT defines exchange correlation functional and grid. TCE specify options for a calculation using the tensor contraction engine, which is very useful, which I will explain. Geometry lists of atoms and coordinates. Self-consistent field specifies the type of wave function and convergence options. Basis defines a basis set for the system. Task executes a specified task. And Python is embedded. in the code to control NWChem. Charge sets the charge of the system. Set modifies the value in the DB file. Unsets delete a value in the DB file. Stop stops the NWChem calculation. And then we have dir dyv tst option that runs polyrate calculation using methods in NWChem. So what are DB files? When you run NWChem, it will create a file named input.db. This file contains restart information. Data in the database can be accessed using the set and unset directives. The geometry directive can be specified with Cartesian or Z matrix. Here we have the Cartesian coordinates. Here we have for water molecule the Z matrix, as you can see in the geometry part. And you can fix a variable, meaning you can freeze it, or you can take it as constant. And that is defined here with the bond length between oxygen and hydrogen, R1. We want this not to change in the calculation, and we fix it by saying its constants R1 is 0.95 and should not change during the calculation. So the units, we have atomic units and PM units. Default units are angstroms. And the symmetry occurs within the geometry directive. So you put usually the symmetry information within the geometry block before you end that block in your input file. So an example would be in atomic units for C and H. We put the geometry information and then say that's for a benzene molecule, for example, symmetry is D6H. So the symmetry keyword is sometimes required, let's say for an oxygen molecule, for some calculations on linear molecules as well. When it comes to crystals, the lattice parameters are specified in the geometry directive. The coordinates for atoms and the unit cell are then specified. And you can see here in the geometry option that the crystal is defined with lattice and the angles. And then the geometry is defined. And then comes the basis directive after geometry. Here we had in our example library, star library 321G, star means all atoms. So this will specify the 321G basis set from the NWChem library for all atoms in your input file. So in this example, we want to define we want to use different basis sets for two atoms, for the carbon atoms and oxygen atoms. And for the carbon, we use a smaller basis set, it's 321G, and for oxygen, a slightly larger basis set, which is the 631G. So you can do that in NWChem as well. You can define also your own basis set. Let's say you developed the basis set, you calculated the basis set, and you want to use your own basis set. You can do that in NWChem by giving the input parameters under basis. When it comes to self-consistent field-related options, we have semi-direct and direct integral storage methods, trash for convergence threshold, and max iterations, maximum self-consistent field iterations. So you put that in the self-consistent field options block and end that in your input file. Here we have maximum 30 self-consistent field iterations for a doublet in unrestricted Hartree-Fock calculations. That's an example. So effective core potentials, ECPs, are specified very similar to the way that basis sets are defined. You can call them using the ECP block, but we are calling for all atoms from the library in ECP, for example, and then end that line. ECPs can be also explicitly defined when you want to use your own parameters, okay, your own values. Then we have the tensor contraction engine, TCE. That was developed by Ohio State University and Oak Ridge National Laboratories. It generates a low-level Fortran code for high-level mathematical expressions. It's used in NWChem to generate code to perform various high levels of ab initio theory calculations. So the tensor contraction engine section in NWChem allows many calculations, including Muller-Placid second-order perturbation theory calculations, coupled cluster, MP4, CI calculations, etc., etc. And these can be run in restricted Hartree-Fock, unrestricted Hartree-Fock, and restricted open shell Hartree-Fock reference functions. So the TCE directive syntax looks like this, for example. You write TCE and then you have a coupled cluster calculation and end that, and you say the task is to calculate the TCE energy in NWChem. The tensor contraction engine should be used when? Well, when you cannot do the calculation otherwise. NWChem has more than one way to do the same calculation. The original MP2 CCSD code in NWChem is more efficient than using the TCE. As of version 4.7, original CCSD code can only handle restricted Hartree-Fock reference wave functions. TCE can handle restricted Hartree-Fock, unrestricted Hartree-Fock, or restricted open Hartree-Fock. A few notes about coupled cluster calculations. CCSDT is slightly less accurate than CCSD for many applications, and it's much more expensive. CCSDTQ, which we said last week too, is slightly more accurate, or 2 weeks ago, is slightly more accurate compared to CCSD, and it's incredibly expensive computationally. So scaling of electronic structure calculations, when you look at the scaling factors, it goes from n to 4 to n to 10. So CCSDTQ is very expensive, as you can see. So instead of using atom-centered Gaussian functions, Gaussian basis sets, you can also use plane waves in NWChem. Plane waves provide a systematic way to improve a basis set, and plane waves are lousy at describing the rapidly changing electron density near the nucleus. Pseudopotentials are almost always used, even for first-row atoms. These methods are often used for calculations on bulk solids, but I use them also in solution phase, in aqueous phase, for example, with some tricks. So plane waves, that's the option with NWPW. You define the energy cutoff, exchange correlation functional when you want to use DFT, evals cut, and then end it. And the task here is to calculate the plane wave energy, for example. So if you want to generate a pseudopotential, you can do that too. Let's say for the element iron with a charge 26, right? That's the option to generate a pseudopotential in NWChem. And when it comes to DFT calculations, we have the DFT block in our input file. We define the grid, what kind of grid we are going to use, and then the exchange correlation. And here the task is to calculate the DFT energy, for example. DFT functionals are available, and many different versions are appearing after version 4.7 in NWChem. When it comes to correlation energy, By default, no orbitals are frozen. So in MP2, you can freeze the atomic orbitals and end it. In CCSD, you can freeze the atomic orbitals and end it, for example. Freezing, when you want to freeze a few orbitals rather than all orbitals, you can say freeze core 1 or freeze virtual 2 in CCSD or MP2 calculations. And then we have the RO-MP4 correlation energy. That's under TCE, better actually. And the task is with restricted open Hartree Fock, because we have restricted open Hartree Fock, that's why TCE would be better, is to calculate the task energy. CCSD-TQ using TCE, number of processors, wall time and speed up is given here, and it's still very expensive in my opinion. And then you need to also not forget to specify the memory usage in your input file. So here are some examples on how to define the memory. And memory, while individual routines allocate the memory. Program will crash if it gets to a routine that asks for too much memory. NWChem usually will give a good error message and define the error in your run. If you're running the job in parallel, there will be many MPI errors that will follow. So when it comes to input and output, large QM calculations require tens or thousands of gigabytes of temporary storage. The default I/O scheme in NWChem is to use a global array virtual file. Several other disk I/O schemes are available if your calculation requires more memory. And Python is an interpreted language like Perl and can be used in NWChem to manipulate values from the DB file and anything else you can program in Python. And you can print even Python hello world and end it in NWChem. All Python code is shifted left by as many spaces as there are in the first line when it is sent to the Python interpreter. So here is a Python example. You say print hello world or print hello again, and it prints that out. And it's sent to the interpreter. So when you have, for example, this print option on the right side a little bit rather than on the left side, it will go to the interpreter differently and NWChem will die. Identification must be the same that of the first line in Python. So you can call the NWChem routines from your Python script, like when you have task energy to run a couple cluster calculation, or if you wanna you do some energy calculation. Let's say here is an example. To run not only one single job, but to run multiple calculations on the same system, you can simply insert additional task directives and change other variables when needed. Calculations will be performed in the order they appear in the input file. So it will first calculate the DFT energy, and then it will calculate the Hartree Fock energy. In multi-step jobs, you don't have to use always lines, but you can use also semicolons. So let's say you have an MP2 calculation where you freeze the atomic orbitals, then end it, and task is that you calculate the MP2 energy. Or you can freeze some certain atomic orbitals like freeze core 0, end it, and task is again to calculate MP2 energy. So this is it regarding NWChem, and today we will go into a little bit of advanced level. So these slides were prepared by Mikael Johansson, and I love the slides, so I wanted to show the slides to you too today. And we will talk about the advanced options here. We started simple, but you all became more experienced in quantum calculations now, also a little bit more experienced in MD or MC simulations if you want to run classical molecular mechanics. We talked about that last week a little bit. We will talk about it more when we use GROMACS. So the objective here is today to learn how to compute electronic excitation energies at density functional theory and the coupled cluster levels using the NWChem program, as well as visualizing how the total electron density is changed upon excitation. And we will talk about time-dependent DFT excitation energies, computing electronic excitation spectra, let's say from UV-Vis, right? Is these days possible for large molecules due to efficient implementations of time-dependent density functional theory. Despite the name, the most common usage of TD-DFT is to compute excited state properties within the linear response framework. In the case of excitation energies, no time dependence is actually modeled. Note that with excitation energies available, also excited state potential energy surfaces are available. With modern software and hardware like NWChem, TD-DFT calculations can routinely be performed for molecules with hundreds of atoms. The quality of excitation energies obtained by TD-DFT depends on the exchange correlation functional used. Relative excitation energies are reproduced better than absolute values, and hybrid functionals usually perform better compared to GGA functionals. The part of exact exchange that hybrids include help correct for the wrong asymptotic behavior that most functionals suffer from. Long-range corrected functionals usually fare even better. Generally, the results obtained by TD-DFT have been found to be satisfactory, especially considering how computationally cheap they are to compute. They are fast. So there are some special categories of excitations that approximate functionals describe quite poorly. Conical intersections at the excited potential energy surface, their multi-reference treatment would be necessary. Excitations that have double excitation character, Rydberg excited states, and charge transfer excitations. In charge transfer excitations, the incoming photon excites an electron, which then moves over a large distance in the molecule. Standard TD-DFT severely underestimates these excitation energies. A good overview is presented by Martin Hedgarden in JAGS from year 2004, if you want to read this paper, actually. It's a very interesting paper. So when it comes to self-interaction error, and I had a question beginning this course today, when it comes to self-interaction error and delocalization error, the Coulomb term in both density functional theory and Hartree-Fock contains an unphysical interaction between an electron and itself. So you see that here. With this unphysical interaction, the effective Hartree-Fock cone-Sham potential is the same for all orbitals. In Hartree-Fock, this is not a problem, as this is exactly cancelled by the exchange term. In Cohen-Sham density functional theory, with approximate functions, the exchange correlation energy usually does not cancel the Coulomb self-interaction. Okay? So when we have one electron SIE, when we consider the hydrogen atom with just one electron, for example, and here are some of the results using hybrid DFT and compared to Hartree Fock. Almost all approximate functionals suffer from self-interaction error. Note energies below the correct answer of minus 0.5 Hartree. Note also different Coulomb energies between methods and different densities. To minimize Coulombic self-repulsion, delocalized orbitals are unjustly favored. Two diffuse orbitals with self-interaction error, actually. SIE present in both exchange and correlation functionals. Do not forget that. So here is a nice paper published by Young. It goes into the insights into current limitations of density functional theory that was published in 2008 in Science. And how reducing this error will open new frontiers for applications of density functional theory. It's a nice paper if you want to read it, actually. These are challenges in theoretical chemistry. So when we want to look at the dissociation of the hydrogen cation, a rather embarrassing case for density functional theory appears here. Qualitatively wrong dissociation of the one electron system in the cation appears when you look at the results, actually. And in general, DFT is always a problem with dissociating radical ions as well. So other practical consequences of self-interaction term in DFT. Occupied orbital energies are too high, from HOMO to low. Band gap is too small. Sometimes Aufbau principle cannot be satisfied. Problems with anions, HOMO orbital energy can become positive. That is, it's unbound. Self-interaction introduces non-dynamic correlation. Exchange functionals in DFT have been found to introduce correlation that in the terminology should not be treated by exchange. Mild multi-reference systems can for this reason be treated quite well with DFT, much better than with lower order WF correlation functions. SIE corrected exchange functionals seem to include no electron correlation. So more problems posed by SIE, what are these? Reaction barriers can become too low, especially for atom transfer reactions. Wrong asymptotic behavior of the exchange correlation potential. Approximate functionals vanish exponentially, meaning too fast, instead of this equation that we have here. Negative ions often are unbound. Occupied orbital energies are too high, and polarizabilities of long chains are overestimated, especially for conjugated pi systems like the example shown here. So, when it comes to TDDF energies, excitation energies, the problems with Rydberg excited states and charge transfer excitations can be traced to the self-interaction error and the wrong asymptotic behavior of the exchange correlation potential. So when the distance goes to infinity, the excitation energy of a charge transfer excitation should be equal to this equation, whereby IP is the ionization potential and EA is the electron affinity. Due to self-interaction, the ionization potential is too low and the excitation energy is too low as well. The excitation energy computed by density functional theory is exactly the energy difference between the orbitals involved in the CT transition. In molecules, the exchange correlation potential of semi-local functionals decay exponentially. The exact exchange correlation potential should decay as -1 divided by R. Hybrid functionals are a bit better, decay where we have the amount of exact Hartree-Fock exchange implemented. So then we introduce long-range corrected functionals, right? So hybrid functionals improve the form of the exchange correlation potentials at large distances. And pure Hartree-Fock exchange is not a good idea, as we discussed. How about changing the amount of Hartree-Fock exchange depending on the interelectronic distance? This would give the long-range corrected version of DFD, which has the abbreviation of LC-DFD. Also rate-separated functionals. LC functionals partitions exchange into short and long-range terms smoothly using an error function. Short-range exchange described mostly by the normal function, typically by 0 to 25% Hartree-Fock exchange, and long-range exchange is described mostly by exact Hartree-Fock exchange, typically by 65 to 100%. So, when we look at long-range corrected functionals, LC functionals, partitions exchange into short and long-range terms smoothly using an error function. The attenuation parameter mu, sometimes omega, defines how soon full Hartree-Fock exchange takes over typically, which is 0.3 to 0.5, usually fixed, and it yields better results when it's dynamic. This leads to much improved excitation energies, among other things. However, when it comes to coupled cluster excitation energies, the singles and approximate doubles coupled cluster model, CC2, is an alternative to TD-DFD for computing excitation energies on large systems. While it's not as fast as TD-FT, quite large systems can already be studied using CC2. Of the wave function-based methods of computing excitation energies, it has arguably the best price and performance ratio. It can describe charge transfer excitations. There are still problems with double excitations, but you can get a diagnostic telling you if it's a problem or not. For a bit of background and illustrative example, please see the paper by Cohn and co-workers, where they studied the intramolecular charge transfer mechanism in quinolidines. And they described that very nicely there. It was published in 2006. Well, today, we will compute excitation energies with the full CCSD model, and at least in principle learn how to compute also CCSDT excitation energies. So let's go through some of the basic usage of NWChem again, the program of choice today again. So here, I showed you before the website and the GitHub site. You will find a lot of information there, including the manual and tutorials and examples. Here, we will not really go through how to use NWChem in general. We went through that already, but rather focus on how to get the program to compute excitation energies at DFT and coupled cluster levels. The input structure is quite clear. There are, however, plenty of undocumented or poorly documented options in NWChem. So first you need to set up the environment when you want to do your calculation, but this is all done for you in Truba. We did that already 2 years ago. And After that, you can set up your calculation. So we will first go through a few input examples interactively, and then you can run them at home and continue with the actual exercises. Our system of interest today is 18-fluoroethene dimer, and this is separated by an appreciable distance. It's a bit artificial, but contains a prototypical charge transfer excitation between the HOMO and LUMO orbitals. We will test how these three levels of theory describe the excitations in the system. So we will have standard DFT, long-range corrected DFT, and CCSD today on this system. So first, example first. The first example would be TD-DFT energy calculations at Purdue Berkeley PBE level, Purdue, when I could speak today, Arts and Herf, with a def to SVP basis set. So we say start, we give the title, we give the memory, we give the geometry, we give the symmetry, we end the memory part, then we select the basis. We select def to SVP as given here, and the basis part, and then we do from the library, Vegant column fitting and end it. And from there on, we go into self-consistent field direct and end it. And the DFT calculation that we are going to do has these exchange correlational, a convergence energy. The vectors output would be here with this file name, and then it goes into the TD-DFT options where you define the values for your system, and then you say at the end task is TD-DFT energy. So the TD-DFT energy gradients at PB-DEF2 SVP level for getting excited state densities, that would be next example, we need to compute the gradients of the specific excited state in question. Well, you should note that only for one specified target excited state at a time can be calculated. With gradients, one can also optimize the excited state geometry by changing task DFT gradient into task DFT optimize. Optimizing excited state geometries is much more complex than optimizing GS structures. However, one difficulty is that one has to specify which excited state to optimize. But the energy order of the excited states can often change during the optimization as the structure changes, right? You are familiar with it anyway from our examples too. So how it looks like is now we have everything else is the same. We have the geometry, symmetry, basis. We have the Vegant Coulomb fitting from the library. Then we have the self-consistent field. Now in our TD-DFT, and we have the target symmetry and symmetry as well. And the task DFT became gradient rather than energy. Okay. So you can visualize the movement of the electron upon excitement. G-plot module takes care of preparing grid-based 3D data. We will use it to output Gaussian cube 5 format, as this format is widely recognized by many visualization programs. To get the electron density difference between the ground state and the excited states, we need to make a 2-cube file, one with the GS density and the other with the ES density, and then take their difference, ground state and excited state, right? To get NWChem to create the cube files, we need a few additional directives to the end of example of the second example. For the ground state density, we write dplot, we give the title, we give the vectors that we calculated, we give the spin, and then the x, y, z, and then from Gaussian, we define the cube output and that, and we say task dplot. And then it will plot us the movement of the electron upon excitement. So for the excited state density, it looks like excited state density matrix is going to be used. Then we put the XYZ and then define the output cube file and say task dplot. There are many tools that can manipulate cube files, but this is going to be too advanced. When you are interested, you can look into this web address that is written here. And I will be sharing the slide with you anyway, so that you can have a look into that. So then let's load the resulting cube file, and it looks like this. With JMOL, and look at the transition, right? How do you do that? You type in JMOL c2.cube. Then in the JMOL script window, you can see the ISO, you can set up the ISO surface of positive cutoff and negative cutoff. And then you can see how the movement of the electron upon excitement is occurring. So in EOM CCSD calculations, these require a lot of memory. So it's better to increase the number of nodes in order to not to run out of memory. Another parameter that heavily influences performance and memory requirements is the tile size parameter of the TCE block, which I explained just 30 minutes ago. The higher the value, the faster the calculation, but the more memory the calculation will require. The related parameter at tile size should be larger than tile size. EOM CCSD is done with the tensor contraction engine model of NWChem. Some comments on some parameters are EOM MSOL2 is faster and less memory intensive than the default solver EOM SOL1, but doesn't really work for double excitations because it uses a CIS for initial guess. The threshold CCSD ground state equations is converged usually 10 to minus 5, which is very sloppy, but the EOM excitation energies only to 10 to minus 4 here in this example. The later setting only works with EOMSOL2, okay? And then DIIS 8, these are the DIIS iterations, like we showed that also in games, for excitation amplitudes should be larger or equal to 5. Sometimes playing around with this avoids convergence problems. And plenty of other parameters are there to tweak and tune in the tensor contraction engine module of NWChem. So if you look at the input file again, it looks like this. You define the memory, geometry, basis. You're familiar with all of this by now. And then under TCE, after self-consistent field, under TCE, you have the CCSD option and tile size, at tile size. Here we froze the core atomic orbitals. We define our threshold, EOMSOL2, DIIS to 8, as you can see. And we set the TCE threshold to 10 to minus 4, as we spoke about that. And task is the TCE energy calculation. So you can also calculate electron densities at the coupled cluster SD level. This functionality is still quite preliminary and almost undocumented. Some apparent limitations are that it only works without symmetry. Frozen orbitals cannot be utilized. It does not work with 2EORB, 2 electron integral scheme, because it needs too much memory. But we will have a look at it anyway. So how does it look like? Computing the ground state CCSD density. So you define the memory geometry, which includes your symmetry, and the symmetry is C1, as you can see, because you cannot define the symmetry. Basis set is chosen, then SCF. In CC, you define your parameters, and task is TCE energy, and then you can plot the ground state density functional matrix. Your XYZ is given, and the output is in cube format, and say task D plot. So when you do that, and you calculated that part of the calculation and to compute an excited state CCSD density, how does it look like? Well, the difference is that we have a threshold of 10 to minus 4 here under TCE option. Everything else is almost the same, except the titles, etc., are different, right? And here you can plot it also with the .cube file and end it with, after energy calculation, with dplot, the task. So when you compute the excitation energy of the HOMO-LUMO CT transition using a PBE functional, and compare the excitation energy of this transition with the energies of the density Hartree-Fock HOMO and LUMO orbitals, what do you observe? So when you plot the HOMO and LUMO orbitals using appropriate dplot comments at home, for example, by running these examples, that's what I would do anyway as a homework from today's class, actually, if you are interested in it, because you will have an understanding about the excitation energy of the HOMO-LUMO and this transition energies of the DFT HOMO-LUMO orbitals, and how to plot the HOMO-LUMO orbitals using the dplot comments. So if you need more than the default 2.6 gigabyte per core for you, NWChem calculates on CISO, you need to edit your job script to use only a fraction of the cores per node. For around 5 gigabyte per core used, for example, you can define the following. For large TCE calculations, that means larger systems or larger basis sets or both, more cores can help if memory is limited. There is also plenty of things to tune with the memory parameters, and it's beyond this tutorial today, but adding these to the TCE block is a good start. And here are the options to do that, right? And that's explained in the manual as well. So this was it for today. We are done with NWChem. I explained the theories, of workshop, but in games as well when we did that. And today we talked a little bit about Hartree-Fock to DFT, Hartree-Fock to DFT comparison and TD DFT and coupled cluster calculations and NWChem and the theories behind them. So if you do not have any questions, I would say we are done for today.